Okay, let's get started again. Okay, so again, our goal is to show that you can't get this. Well, you want this to be close to x for all values of x. On the other hand, it's not going to be different from this, which doesn't know about x, unless you call the oracle many times. That's going to be the structure of the proof. So we define a discriminator as that just measures the difference between these two. And a global discriminator, which is just the sum over x of the local discriminators. And the first thing we want to show is that this discriminator can't get very big unless we make a lot of calls to the oracle. So again, the intuition is that the oracle is kind of a wimpy operator, and so to make it make a difference, you have to call it many times. Okay, and the proof is by induction, and I'll go through this one in some detail. But I won't go through the algebra of all the subsequent steps because it gets pretty. Okay, so the difference between, we're looking at the local difference between phi j plus 1 x and phi j plus 1. These guys okay, you might, okay, this has only a j because both we could have included a u j plus 1 on both of them, but since j plus 1 to make the equality manifest, but since u j plus 1 is unitary, it doesn't affect the magnitude of this difference, so we just get rid of the u j plus 1. So this is indeed equal to the definition of the local discriminator. And now this is equal to sum on x of O sub x. We break it up into pieces which display the differences between the wave functions and the wimpiness of the oracle, like this. And now we can expand this out. We'll have two direct terms, which are squares, and one cross term, which we can bound using the Cauchy-Schwarz inequality. So this is equal to or less than the sum on x, OX I'm sorry, xj minus and here's where you use the Cauchy-Schwarz inequality. This is actually, have we even used Cauchy? Yes. No, I'm sorry. We haven't used Cauchy-Schwarz yet. We're just using the triangle inequality that says the cross term is less than the product of the magnitudes of its components. We'll use Cauchy-Schwarz momentarily. Like that. And the notation a little more clear. Okay, now O is a unitary operator. So again, we can get rid of this, get rid of that. And then we recognize that we've just got d sub j when we do the sum. So there we're using the inductive step. O sub x minus 1 is just 2 times xx. By the definition of the oracle. And then when we sum over x, we can use completeness. So this sum is just 4. It's twice the magnitude of phi j squared. And then this one, now we use Cauchy-Schwarz inequality that says inappropriate notation. In fact, with a 2. What's that? There's a 2, yeah. So, and that gives us what do I have? Sorry here. Oh, okay, so we haven't used this. So this is just, again, appealing to the unitarity. This is just and now we use Cauchy-Schwarz because these are things whose squared magnitudes we can estimate in terms of things we know, basically using these same arguments that we had up here. And this becomes, this thing is equal to or less than 2 square root of dj, because when we take the magnitude of this thing squared, it's just our 4 again, and the square root is 2, and this one is giving us dj squared. This one. Again, because O is a unitary operator, we can get rid of it, and we just meet dj again when we take the squares and sum over x. So altogether, this is equal to or less than dj plus 4 plus 4 square root of dj, which is, since we've assumed that dj, by the inductive hypothesis, that dj is less than 4j squared, this is 4j squared plus 4 plus 8j, which is indeed equal to sorry, the board isn't bigger, equal to 4 times j plus 1 squared. And that gives us the inductive step. Okay, so we show that that discriminator can't be big until k gets big. And now there are two more. So now the next step in the proof is to write the discriminator in a different way. We want to exploit the fact that phi k of x is getting close to x in some sense. So we write this as, whereas psi sub k without the x isn't for all x, we don't expect it to. So we write this dk like that, just adding and subtracting x. And then we want to show that this one is getting small, this one is not getting small, so dk can't be too small, and therefore, and that's going to run into the fact that dk can't be too big either unless k gets big. Okay, so implementing that strategy, it's useful to define intermediate quantities, e sub k, which is the sum on x of psi k minus x squared, and f of k equals sum on x of psi k minus x squared. And then we bound E and F separately. We've bound E. Okay, we assume we're getting a good answer. That's okay. If we don't care what the answer is, we can do anything. Okay, but the whole point is we want to be converging on an answer, and this is where finally we make reference to that fact. So we want to assume that the overlap between phi k of x and x is equal to or greater than a half, say. You could put in any number with simple modifications of the proof, but a half is okay, is a fine number to put. And now a subtlety, which I missed in the notes, but I'll correct in a version that I'll post very shortly. If you adjust things, if you adjust the phase of x so that phi k x is real, okay, and we can certainly do that. We're allowed to add and subtract anything we want, and so we can add and subtract the adjusted x. Then you can show, and I'll leave it as an exercise, that ek is the sum of these terms and we have the direct terms and the cross terms. The cross terms can't be too small, so they're going to make a significant subtraction to the direct terms, and just carrying through the numerical aspects, you find that this is equal to or less than n times 2 minus square root of 2. Okay, the square root of 2 comes from the cross term having a factor of 2, and then at least a 1 over square root of 2. So you're subtracting off at least that much, and therefore you arrive at this upper bound to ek. Okay, in the notes I didn't make reference to this phase adjustment, so you'll find it very confusing at that point, but it's not a serious difficulty. You just do have to make that adjustment. Yeah.
In the definition you take, so the size of x subatory minus the state.
Yeah, minus the number state x, which was the answer. Remember.
And besides
Psi k was the thing where you started with the reference state and acted with the u's and the oracles, k times. This one was where you acted with the u's but didn't use the oracle. Okay. Then on the other hand, you can prove that f is not terribly small basically because in the sum on x, you reconstruct the state s. The x's all point in different directions, and the psi's, which don't know about those different directions, can't have a coherent product. And so you can't get too big a cross term. In any case, I'm not going to go through that algebra. It's very simple and shown in equation 12. You can show that f is equal to or greater than 2n minus 2 square root of it. So E can't be too big. I mean, they're both close to 2n in some sense, 2n, but E can't be too big and F can't be too small. So their difference can't be too small. Yeah. On X? Well, we don't know how psi k depends on x offhand. Well, I'm sorry, psi k doesn't depend on x at all. But it's very important to do the sum, because so that the x's are still there. And in fact, okay, it's important that in the sum, in the cross term, there's no x dependent here. There is x dependence here, but because there's no x dependence in this one, you can add up all these x's in the sum, and the key geometric point is that they're all pointing in different directions, so that S is not a very big vector. The sum is not a very big vector, and so it can't cancel off too much of psi k. In fact, it's a very small vector compared to how many terms it has. That's where the square root of n, this could have been n, but it's only square root of n because of that. Okay, so, and then again, I don't want to bore you by reproducing the algebra that's in the notes. By expanding this out using Cauchy-Schwarz again, you show that this dk is equal to or less than square root of ek minus square root of fk squared. I'm sorry, equal to or greater than. There can't be too much cancellation. And for large n, and in fact for all n, you find that this leads to dk equal to or greater than 2 minus square root of 2. So we have on the one hand, dk is equal to or greater than n times 2 minus square root of 2. On the other hand, it's equal to or less than 4k squared. The only way these can be reconciled is if k is of order square root of n. Which is what we wanted to prove. You need square root of n calls to the oracle in order to solve the search problem. So that concludes the second part, the demonstration of optimality. It's very unusual, actually, in design of algorithms that you can prove both upper and lower bounds, but this is one case where you can. Yeah. It has to be at least square root of n.
At least?
Yeah.
Oh, yeah, sure.
Maybe I... Well, the basic step is j equals 0 is trivial. The initial steps are trivial. Yeah. Yeah. So. Yeah. Okay. So as I said at the very beginning, there's good news and there's bad news with the Grover algorithm. The good news is it's really interesting. And it does show clearly a case where the quantum computer can do something that a classical computer can't. For equal numbers of gates and processing speed, the quantum computer has a definite advantage, qualitative as well as quantitative advantage. You go from n to square root of n in the search problem. On the other hand, going from n to square root of n is not a huge step. If you went from big N to little n, that would be something to get excited about. Or that would be a turning exponentials into logarithms, or of course, if you could eliminate any n dependence, that would be even better. But that's not what we have here. If you could do either of those, you would show that quantum computers turn these difficult NP problems into easy problems, things that don't take a lot of time, and that would be a revolution. Okay, then it would be advisable to start a crash program like the Manhattan Project to build a quantum computer. Okay, but that's not what's found. In fact, under the assumptions of this proof, you just find a quadratic speedup, which is interesting, but given the difficulty of making a quantum computer with many gates that has a reasonable clock speed, it's going to be a long time before this is of practical use. So, and I should say that historically there was a lot of optimism in the early days of quantum computing, before this was clearly understood, when a different algorithm, the so-called Shor algorithm, was discovered, which allows factorization of large numbers in an exponentially faster time, basically, than classical computers can manage, under the same parameters of comparison. So that led to tremendous optimism that all kinds of problems would be solvable rapidly using quantum computers. But this has been a big stumbling block to that. And in fact, very few cases are known of concrete problems where quantum computers are actually useful, or will be useful in the reasonably near-term future. Okay, so what could we question about this proof? What could we? It's a proof based on discrete circuitry. And there's another paradigm of quantum computing where by discrete I mean circuitry that steps through a program in discrete time steps. Okay, that's of course the way top of the line computers, classical computers work today. There's a clock that runs the whole thing and everybody's synchronized. You go step by step. But there's another paradigm of quantum computing, which is called adiabatic algorithms. And here the idea is that you use your circuitry to construct a family of time-dependent family of Hamiltonians. Let's say, for purposes of argument, we use two different Hamiltonians and phase, one in and one out, as a function of time, just to be definite, I'll write down. Where H1 has the property that its ground state is something we can easily construct, like our reference state S, something that accesses all the possible states of the answer with non-zero weight and is easily constructible. And where H2 is constructed so that its ground state is the answer. So in the search kind of algorithm we've been discussing, H2 could be something like minus A0, A0. So A0 is the ground state. And it's not difficult to design, given an oracle, not difficult to design a circuit that produces this Hamiltonian. And a Hamiltonian for which S is the ground state. Which one is not right? Oh, I think I want to reverse these, I guess, is what you're saying? Yeah, I think I want these in the opposite order. So. And just to normalize things, let me also do it this way. If I were Fermi, I would say, well, I was planning to run it backwards, but no, it's just a mistake. Okay, so at t equals 0, we start in a known state. At the end of time big T, we want to be in the answer. If we do things nice and slow, and such a way that we stay in the ground state the whole time, making use of the fact that in quantum mechanics, states of the same symmetry don't cross generically. Following the, if we do it slow enough so that the adiabatic theorem applies, we will evolve from our known starting point into the desired answer. So that's the basic idea of adiabatic.
How do you know you're going to the ground state at the end of the...
That's the, you stay in the ground state all the time. It's because there's no quantum jumps. That's the adiabatic theorem. You start in the ground state, evolve slowly. As long as the gap doesn't close, you stay in the ground state. But the fly in the ointment here,
The answer is the state, not something measurable, observable.
no, then
There's a
the,
phase
you,
involved that may depend on the trajectory.
a phase? Yeah, phase doesn't matter.
Phase doesn't matter. Okay.
The phase doesn't matter because, and remember, at the end, we're just going to evaluate on all little n registers whether they're 1 or 0 to get the binary number that represents A0. But the difficulty here is that even if the levels never cross, they might get very close. We may need to evolve very slowly And so this is not guaranteed to be a fast algorithm. So for instance, if the levels get as close as 1 over square root of n, in appropriate units, then it's going to take us square root of n. We have to go no faster than square root of n, and we're just as slow as before. Okay, so there are 3 possible reactions to this. One is design your Hamiltonians carefully. So that the levels don't get close. Another is kind of a brute force thing, which is when you do a quantum mechanical evolution, the thing that always appears is h dt, integral of h dt. So if you just scale up the energy of everything, and keep things otherwise the same, you can scale down the time. And so if you're willing to put a lot of energy into your calculation, you can do it faster. Just saying you scale up the whole thing, including the distance at the minimum distance of energy approach, and so you can speed up your adiabatic evolution. And to discuss how realistic this is in different applications, you have to put in numbers and physics. You know, if you want to have a list that's 1 billion things long, and you're hoping to undo this 1 over square root of n, for instance, you have to have whatever your original energy scale was, scale it up by 10 to the 5th. It is.
You have that characteristic, the generic energy scales. You cannot go and increase the energy, keeping the same structure by, I don't know, a factor of many orders of magnitude.
Yeah, I agree.
It's not
I agree. This is kind of, this is a point of principle, I guess. Just to show, well, okay, this is really a point of principle. I sort of set the stage for it. There are formal demonstrations in the literature that the adiabatic approach and the discrete time approach don't give fundamental differences in rate. You can simulate an adiabatic evolution using discrete circuitry accurately. However, that demonstration, which I must say I don't understand, obviously has holes in it because it doesn't have room for this phenomenon, as far as I can tell. So there's something missing in that demonstration that could be very important. In any case, it seems a fundamental point worth making that you can just scale. If you're willing to close your eyes about how realistic it is, just scaling the energies up enables you to decrease the times. Maybe you have to go from atomic systems to nuclear systems, or I don't know. But in any case, It's I think, a very important point of principle. And then third, you might introduce dissipation. If you want something to stay in the ground state, a very good way to do that is to allow it to dissipate energy into the external world. Now, as far as I know, this hasn't been studied very much. I just kind of thought about it a little bit while I was preparing this lecture. But it seems like a good idea. The challenge, of course, is to make sure that your dissipation is controlled. You don't want to spoil the good features of the quantum evolution too much. Okay. But introducing dissipation tastefully, especially at the moment when the levels were close to crossing, might be a good approach. And this definitely is outside the framework of any of the theorems that I could tell, which is along these lines, I should mention, and I'll conclude with this remark, that in lattice gauge theory, which of course is not quantum computing, but classical computing that simulates a quantum system, and has had some spectacular success in doing that. In lattice gauge theory, if you want to find the ground state, with some quantum numbers that you're interested in. So for instance, if you want to find the proton, you put in the quantum numbers of baryon number 1. The trick is you start with a state with the right quantum numbers and apply e to the minus Hamiltonian times tau. So you work, if you like, in imaginary time, and this converges exponentially to the ground state. Not nearly as fancy as Grover's algorithm, but also manifestly powerful. In fact, if you think about it, the tricky thing about Grover's algorithm, the thing that made it difficult to find the answer, is that the information about the answer had to appear in a unitary operator and the biggest contrast you can get in a unitary operator between one state and all the other states is a relative phase of -1, which in fact is the oracle we assumed, just a relative phase. That's hard to work with, and the whole trickery of Grover's algorithm is to work with that phase information, turn it into an amplitude information, and get the answer from that amplitude information. If you could directly get amplitude information, if you could have -1 plus epsilon instead of, or -1 minus epsilon instead of just -1, then you could iterate and get to the answer in this style. So somehow it's the restriction to unitary operators that makes things so hard. If one can relax that even a little bit by making intermediate measurements or by having some dissipation, I think there's reasons for optimism. that you could do better. Okay, but that's speculation, and this is I think this wraps up what I wanted to say about quantum search. We're continuing to think about it. Okay, okay, are there any questions?